Okay, so we come to the final presentation, which is by Hidetoshi Nishimori from Tokyo Tech on analyses of non-stochastic Hamiltonians by the mean field theory.
So thank you very much. I will talk about the effects of non-stochastic Hamiltonians on some simple models. And this is a piece of work done in collaboration with those people, Yuya Seki, Beatrice Seoane, Yuki Susa, Johan Jedbeck, Kabuki Takada, and Masaki Okuwa. All of them are in my group in some sense, and postdoc students, former students, and former visiting students. So all the work they did, I just talked with them. I didn't use my hands or brain, I just used my mouth. So that's the situation is. So my style is to state the conclusion first, so that you can safely fall asleep. So the conclusion is the following. Non-stochastic Hamiltonians are effective to achieve an exponential speedup over stochastic counterpart in some cases. In a few cases, that's the conclusion. And I will try to convince you what this means. And some of you may have already known those results. The oldest paper in this direction appeared almost 5 years ago by Yuya Seki. And I will give you a brief introduction of what's new. We have backed up some of the results by analytical or exact methods, in the sense that the already known results were partly numerical, but we implemented that by analytical or exact analysis. And, and also we have shown that non-stochastic effects are related to quantum effects in some sense. And finally, at the last part, I will mention briefly about our work in collaboration with the group in Sissa in Italy, Matteo and Giuseppe Santro, Matteo already presented the poster on the dynamical aspects using diabatic transitions in terms of the Landau-Zener formula. So those are new things. So what's the problem? The first one is a very simple one, already touched upon by many people, including Matsura-san. It's a P-spin model. P can be 2 or larger, but for simplicity, I will take P to be an odd integer so that the ground state is unique to avoid a trivial degeneracy, up-down degeneracy. So it's an infinite range mean field type model. And of course, we know the ground state trivially. So this problem can be solved very easily by steepest descent. So there is no way to beat that simpler algorithm. So I'm not going to claim speed up in a strong sense. It's just a comparison within quantum framework. It's a comparison of the generic stochastic Hamiltonian and non-stochastic Hamiltonian, which can be obtained by adding the XX term with the positive coefficient. So in this simple stochastic formulation, the initial state of quantum annealing or quantum adiabatic computation is to start with just with a transverse field. So all spins are pointing in the x direction, which in turn means that all possible 2 to the n states in the z basis appear with equal probability. So the task is to choose the best one among those many, exponentially many ones. And of course, the best one is the ordered state, perfectly ordered state in the positive x, z direction. And of course, there is a first order phase transition in the course of the quantum annealing. That is, the initial state is like this, and the final state is like this. And if P is 3 or larger, there is a first order phase transition at some S, SC. So the gap at this first order phase transition closes exponentially, which means that the computation time to go through the to go through this transition region is exponentially large as a function of the system size. And the question is, can we reduce this first order phase transition to a second order such that the computation time becomes polynomial? And the answer is yes. It's very simple. You just add this term, xx term, with a positive coefficient, c is a positive coefficient, with an appropriate strength. This Hamiltonian is non-stochastic in the sense that the matrix representation which diagonalizes the z basis has both positive and negative values. And there are two parameters now, s and c. So let's just rewrite those parameters using another variable. It's lambda. So I rewrote c as s times 1 minus lambda. And I multiplied lambda here for convenience. So this is the problem to solve. And the starting point has s equal to 0. So this term and this term both vanish. So the initial Hamiltonian is the same as before, all spins pointing in the x direction. Quantum ferromagnetic state. And the final state, we have s and lambda both equal to 1. So this term vanishes, and this term vanishes as well. So just the cost function remains. And the initial time has s0, lambda arbitrary, because if s is 0, lambda disappears. So we have two parameters, s and lambda, which should be controlled this way. So that we have phase diagram in terms of s and lambda. So initially, we are somewhere here, s0 and lambda arbitrary. And finally, we have both s and lambda equal to 1. And the stochastic case does not have this term. So lambda should be tuned to 1 along this line. So as I said, along this line with a stochastic Hamiltonian, there is a first order phase transition for P3 or larger. And the question is whether this first order transition persists to the middle of the phase diagram to reach this line. And if this first order phase transition persists across this phase diagram, then there is no way to avoid it. And if this first order phase transition terminates somewhere in the middle of the phase diagram, then we can find a path to avoid it. And the answer is positive. By a quantum statistical mechanical analysis, it is relatively straightforward to draw the phase diagram of this problem in the thermodynamic limit, in the system size infinity limit. And the answer is here. It doesn't work if P is 3, but it does if P is 5 and larger. So if P is 3, the first order phase transition persists from here to there. So there is no way to avoid it from here to there. However, if P is 5 and larger, 5 and 11, for instance, this first order phase transition drawn in red terminates somewhere around here in the middle of the phase diagram. And it is replaced by a second order phase transition drawn in blue. So in this sense, non-stochastic Hamiltonian is very strong, is very effective to reduce the computational complexity from exponential to polynomial. In this sense, it is an exponential speedup by the non-stochastic effects. So this is a phase diagram drawn in the infinite size limit obtained by the statistical mechanical analysis. But system size is finite in computation. And we should confirm that the gap actually closes exponentially here and polynomial there. And that we did numerically. Not we, but USAK did. So at the point on the second order line, he calculated the energy gap as a function of the system size. This is a log-log plot. So those straight lines mean that the energy gap closes polynomially, as expected. And somewhere on this first order line, numerically, he showed that the gap closes exponentially. This is a linear n and log of the energy gap. So it's exponential. So we have confirmed those statements numerically in this sense. So this is a relatively old work. But the new thing is that we confirmed it analytically. This is an undergraduate project work by Okuwa. So this is the same phase diagram for P11, lambda, and S, and the first order line and second order line. Forget about those dots. And we carried out WKB semi-classical asymptotic analysis from the n infinity limit toward finite n, large but finite n. And we could obtain the expression of the energy gap as an exponential form. And we could obtain a very explicit formula for the exponent alpha like this. And forget about those T1, T2, W. They are simple functions of x, something like square root of 1 minus x squared, or something like that. So I don't write formulas for them. They are simple functions. Just believe me. So this is a new result. We could obtain an explicit form of the exponential decay of the energy gap along this line of first order phase transitions. And this curve represents the value of this alpha along this line. So it is almost constant up to here. And as soon as this line hits the second order counterpart, the alpha rapidly decays towards 0. This is the log scale of alpha, and reaches 0 at this point. 0 alpha means that it no longer decays exponentially. And we could also, or he could also show where this is, where this point is. This point is where the first order line disappears in the middle of the ferromagnetic phase. And here is the formula by using some simple idea of the lambda type analysis. So if P is 5 or larger, MC is the value of the spontaneous magnetization at this point, at the tip of this first order line. And MC is a function of P, and so you see, if you give me a P, then we can predict the value of this point precisely. And it, of course, agrees with numerical computation. So this is new. This is an exact result. So this is unpublished. It will be published in a few months. But this is almost a classical problem in the following sense. You see, this is the problem Hamiltonian. And in the problem Hamiltonian, all Pauli matrices show up as a summation of all spins, all sides, from I1 to n. So it is a very big sigma spin. So big spins are almost classical. This guess can be confirmed in the following way. You define the operators mz and mx this way. And you take the computational relation of those operators. Then, since we have two n's here in the denominator, an extra n appears there And My is, of course, defined in a similar way. But, of course, My is bounded. The largest eigenvalue is 1. So if n is put to infinity, the right-hand side vanishes. So these two are commuting operators, which means that they are classical, of course. So in this sense, I can also show you that those two quantities squared sum up to unity. So it is, after normalization, it is like a classical unit vector. So we can replace those operators by cosine and sine. Sine here, cosine here. So it's a classical problem. And what's quantum mechanical? Well, in the following sense. Of course, the phase diagram that I showed you before in terms of lambda and S can be drawn just using this classical Hamiltonian, because that's a thermodynamic phase diagram that is valid in the thermodynamic limit. But such quantum effects around this classical limit is very important. And these such quantum fluctuations correspond to such finite size effects, which is very important to estimate the rate of gap closing. Oh, so it's classical in the infinity limit strictly. And quantum effects show up as a correction to this classical limit. It corresponds to the usual WKB idea of H bar correction. H bar small corresponds to n inverse small or e to the minus alpha n small. So to estimate the rate of gap closing, you should take this effect into account. So in this sense, it's classical plus small quantum fluctuations, but quantum fluctuations are very important. Yeah. Quantum effects, such quantum effects control the performance of quantum annealing or quantum adiabatic computation. Can we quantify those statements in some other way? And the answer is yes. This is the work by Yuki-san, Johann Jedbeck. So we calculated two quantities to verify the statement that I mentioned before. The first one is the trace node distance. Trace node distance is the distance of the eigenstate of the quantum state, quantum Hamiltonian, to the spin coherent semi-classical state. So if this trace node distance is 0, then the eigenstate of the Hamiltonian is purely classical, because the distance to the classical state is 0. And if this trace node distance is 1, then the eigenstate of the quantum state is completely different from the classical state. So this is an important measure to see how the system is quantum mechanical. So we calculated, or they calculated, this quantity along 3 lines in this phase diagram. First, let's set lambda equal to 1 along this line, the original stochastic case for P11 in this instance, as a function of S. And this is the result for various sizes, and 20, 40, and 160. And in this part of the diagram, in this part, everything is flat. So in this ferromagnetic phase, the system is completely classical, as expected. But at the point of phase transition, it suddenly becomes quantum mechanical, just at the transition point, as you see. And beyond that, it becomes a little bit quantum mechanical. But in the thermodynamic limit where n goes to infinity, this set of lines collapse to 0. So for very large system, again, it is very classical, if the system is purely stochastic. This is what we expected already. But the situation changes if we introduce the XX term that makes the Hamiltonian non-stochastic. For instance, if we choose lambda to be 0.1 here, and this line crosses the second order phase transition, the result is here. Again, the system is purely classical up to this point of phase transition, second order phase transition. But beyond that, the situation changes completely. You see, the lines go like this, and we have confirmed that those lines approach finite values anywhere around here. So this is a ferromagnetic phase, but it is quantum ferromagnet. Quantum effects are very important around here. And the same is true for lambda 0.3. So although this is a quantitative change, quantum effects come into play. We increase the strength of the last term, XX term. So in this sense, the XX term with antiferromagnetic sign introduces quantum effects in the system, which should be very strongly related with the change of the nature of the phase transition. I don't say that non-stochastic terms directly induces. No, I should be very careful. Let's go to the next statement. It will be on records. We calculated another quantity to verify the statement that we obtained at this computation. The next one is the quantity called concurrence, which measures the degree of entanglement. Again, the quantumness is measured by this quantity. And we have confirmed that the tendency is very similar to the case of the trace norm distance. Again, here in the stochastic case, everything is classical, except at this point of phase transition. But around here, concurrence remains finite. So it shows that quantum effects play very important roles around here. So these are new results. So in this sense, non-stochastic Hamiltonians, or the XX term with antiferromagnetic sign, induces quantum effects and reduces the strength of the phase transition simultaneously. So this is non-trivial, I believe. And we also estimate the effects of noise from the environment. Time is not up yet. Until 11 o'clock? Okay. So the first line is the same as before. Problem Hamiltonian cost function, which I simplified to write like this, and the transverse field and XX term. And we added 2 extra terms to represent the interaction with the environment. This is the bosonic environment interacting with the system variable in this way. This is a very standard formulation. And assuming that the environment affects the system in a uniform manner over all sides, this is a strong assumption. But we can analyze the system if we take this case granted. And as you see, those spin variables appear once again as a summation over all sides. So they can be replaced by sine and cosine. But if you replace this quantity by sine, then these 2 terms can easily be written as a quadratic term by just shifting the origin of those operators b and b dagger. But these simple shifts of the origin of the operator don't change the commutation relation. So these are, again, bosonic operators. So this term can be separated completely from the system. But we should compensate for the additional term by this minus sign. So this is very important because you see, sine squared appears with a negative sign. Lambda is some positive constant. Then, of course, it's 1 minus cosine squared. Then, cosine squared appears with a positive sign, which adds up to this term, which means that the effects of this xx term is reinforced by the interaction with environment. So in this sense, if we accept this type of interaction with environment, then the environment works positively in the sense that it reduces the first order phase transition to second order farther than the case without interactions with environment. So it is a bit paradoxical, but this is very simple fact. And so jet couplings with the environment enhance quantum effects in this sense. Okay, you already have a question. So I will spend an extra 5 minutes to say something about more non-trivial problems, random systems. A Hopfield model with many body interactions. I don't explain the details about the definition of the Hopfield model, but it is a random system, so it is non-trivial, highly non-trivial compared to the previous one. So it is of course impossible to analyze the problem by the classical methods. So we should invoke the quantum statistical mechanical methods to draw the phase diagram. We cannot use sine and cosine. And we added this term to the Hamiltonian XX term. And I altogether skip the details and say just the results. If this parameter P, which is called the number of embedded patterns in the diagonal Hopfield model, anyway, if this parameter P is finite, then the same result emerges, that this additional term weakens the phase transition in the sense that it reduces the first order phase transition to second order under certain conditions. But the situation changes if P is very large, extensively large. If K is 2, that is, K is the, sorry for the confusion of the notation. If K is now the number of bodies in interaction, which I wrote P before. I'm sorry about it. If K is 2, that is, if the interaction is two-body type, then this method does not work. The first order phase transition persists to here. So it is not versatile, as expected, of course. But if K is 3 and larger, and P is very large, extensively large, then again, we have a reduction of first order phase transition to second order. So the lesson is that XX term works also in the random case. This is highly non-trivial. And this is the second last slide. Sorry about small characters. It will be in the archive in a few weeks of time. This is work by Matteo Walters, who presented this result in the poster. So this is the same problem, p-body interacting ferromagnetic system without the XX term. It is purely about the stochastic case, but dynamics. So we analyzed the behavior of the residual energy. It measures the approach to the correct ground state. Residual energy, the difference between the correct ground state and the actual ground state that was achieved after a finite time t, tau. So the smaller the residual energy is, the better the final state is. It should be finite for finite tau. It should be 0 for tau infinity. And in those cases, simulated annealing gave better results than quantum annealing. But you look at this column for P3 and larger, first order case, and for the case you take n infinity first, then simulated annealing with a final temperature 0 gets stuck. This is the first order phase transition, so the barrier to be overcome becomes infinitely high. So thermal hopping cannot go over it. So a finite value of the residual energy remains 1/2 in this case. This is, of course, what we expect intuitively. What is highly non-trivial is that in the quantum annealing case, the residual energy, even in the thermodynamic limit, it decays towards 0, although slowly 1/log of tau. So the barrier is infinitely high, but it's thin. So the energy reduces towards 0 in the end. So conclusion. First order phase transition can be reduced to second order by the antiferromagnetic XX interactions. So this means that as we confirmed numerically and analytically, exponential reduction in the computational time. And this is non-stochastic and strong quantum effects. But it is not versatile. It's in many cases, it should fail. I showed you one of the examples. And another example is the round field Ising model that I didn't show. It fails in this case. So it is not versatile, but it can be useful in some cases. So this is the end of the talk, all talks of AQC 2017. So thank you to all who attended AQC 2017, plan now for 2018 for AQC. What is AQC? Australasian Quilt Convention. Oh, it's the wrong one. It's AQC, Adiabatic Quantum Computing. So see you next year at NASA Ames. Thank you for your attention.
Okay, thank you, Professor Nishimori. We have time for questions.
So I was impressed that the WKB analysis was able to predict the energy gap. You didn't show the numerical results, but you said that they matched.
Numerical results, yeah. It matches. It does match. We confirmed that at some point in the phase diagram. Yes.
Yes, and I found that impressive. Now I wonder if this was, of course, for the case where all the z terms had the same coefficient.
Sure.
Now in the case where we have different coefficients for the z terms, have you done the WKB analysis for that?
Cost function, the interaction term. What do you mean by the z term?
So yeah, that term. So you did the WKB analysis for that term.
Yeah, sure.
Now in the case where the z operators have different coefficients, the terms in that sum have different coefficients.
That's impossible.
So the WKB analysis won't work anymore.
As far as I know, it doesn't.
Okay.
Daniel.
So something that I found a little counterintuitive, and I'm sure it's just a simple misunderstanding on my part, is why the quantum effects are 0 initially for small s until you get to the avoided crossing. Because we typically say that you start from a superposition state, so you start quantum, and then afterwards, when you pass the avoided crossing, it freezes and it becomes classical. But in your picture, it's the opposite.
That's right. That's right. I agree with you. And I confess I don't have an answer to you. I don't know, honestly.
That makes you feel better.
But this is a fact. Very clear fact.
There's a question here.
As far as I understand, the noise acts globally to your spins. So
Yes,
these are
yes, yes.
GL.
This
But
is
I
a
would say that it's I would say that this GL should be GL and I, and get it inside the sound,
well,
no? Because and then the coherence.
The realistic situation should be close to that, of course. But our motivation was to make this model as simple as possible so that it can be analyzed analytically. So, and one of the excuses is that the noise may affect all the spins uniformly in such a situation where radiomagnetic wave affects the chip whose wavelength is larger than the size of the chip, for instance.
Okay. This I would understand that this makes the GLI similar, of the same order, but still I would put the GLI inside, and then you would have the coherence. So the noise is not going to enhance quantum effect; it's going to reduce quantum effects.
Yeah.
Okay.
Probably, most probably, yes.
Thanks.
So I guess your conclusion is that these non-stochastic interactions can give you exponential speed up in some cases.
In some cases,
but
yeah.
not all. Can you make any general statement about the sort of problems where that is true and the sort of problems where that is not true?
That's the question that I want to know an answer to, of course. I don't know. I don't know. I don't want to make any strong statements.
Fine.
Someone has a question over there.
Yeah. Sorry.
The guy on the web needs to listen to you.
We still online? Okay. This is kind of a related question. So a first look at this, you might think that a physical annealer would need to implement wait for Z interactions in order to see a benefit from non-stochastic couplings. But given that your comparison is always with random Ising models, and when you take a real problem that has high weight Z terms and you embed it into a physical system that only has pairwise Z terms, it's no longer a random model. So is there still hope that we don't need higher weight Z in a physical annealer in order to see a benefit from non-stochastic couplings?
Sorry, I didn't understand your question. Was it a question or comment?
So one of the conclusions you might draw from this is that you need to implement physical ZZZ terms in an annealer in order to see a benefit from non-stochastic couplings.
P should be 4 larger, yeah.
But
for this simple case, but for more complicated case, just two-body interaction may induce fast-order phase transitions.
right, but I guess my
problem.
question is that when you take a real problem that has high weight terms and you embed it into an annealer that only has pairwise Z interactions, it's no longer a random field. And so then maybe there's still a realistic expectation that if your problem has high weight Z terms and you embed it into pairwise Z interactions, that you could see the same effects.
I'm slowly catching up. Yeah, maybe. It's an interesting question to ask and explore in the future. Yeah, thank you.
Thank you.
Any final questions? If not, let's thank Hidetoshi one more time.
Thank you very much.